Hello everyone, this is Ryan with High Desert Math Tutor, and today I want to take a few minutes to talk to you about standard deviation. Now, standard deviation is a way of measuring how much data you have within a certain distance from the mean of a set of data. So let me write down a few different variables. So when we have a set of data, we call the sample mean x bar. That's the common name for a sample mean. Another thing we will be discussing in just a moment is the standard deviation. And the standard deviation of the sample is usually denoted by an S. So what the standard deviation tells us, typically, if we are dealing with data that follows a bell-shaped curve for the distribution, a standard deviation tells us how much data we can expect to be within one standard deviation of the mean above the mean and below the mean. So for example, let's look at this curve that I've drawn right here. So this is a bell-shaped curve, and this represents data that follows a bell-shaped curve for the distribution. From the mean, x bar right here, this is the sample mean. One standard deviation above the sample mean would be the sample mean plus one standard deviation. One standard deviation below the sample mean would be sample mean x bar minus one standard deviation. Now we can do this for several different levels. So let's go two standard deviations above the sample mean. So we have the sample mean plus two standard deviations. The sample mean minus two standard deviations. This is what we need to find two standard deviations below the sample mean. Finally, let's do three standard deviations above and below. So three standard deviations above the sample mean would be sample mean plus three standard deviations. And then three standard deviations below the sample mean would be sample mean minus 3 times the standard deviation. Now, the reason this matters to us, there's something called the empirical rule for standard deviations. So the empirical rule let's see. So the empirical rule says that if you have data that follows a standard bell-shaped distribution, then about 68% of the data will be within one standard deviation above and one standard deviation below the mean. So that's plus or minus 1 S, one standard deviation from the mean. Now, looking at the data we have here, this is equivalent to us looking at the data that is right in this range. So in this box, this is one standard deviation above and below the mean. So right here, the empirical rule tells us that 68% of all of the data we are considering will be in that shaded area under the curve. Now I'm going to extend this, so I'm going to take away these bars for a moment. Now, the empirical rule has two more levels. It says that about 95% of the data will be plus or minus within plus or minus 2 standard deviations of the mean. And then about 99% of the data. And if you're working out problems, you may want to double check. Sometimes books say about 99.7%, but you just have to double check to be sure. Will be within 3 standard deviations of the mean. So what we do here is let's look at 2 standard deviations below the mean. Follow this line here. Now, within this extension of the box, this area represents the data that is within 2 standard deviations below the mean. Now, if we look at the data above the mean, I'll do this. This one doesn't have to be so tall. Completing this, I will shade in the 2 standard deviations above the mean. So right here, the second level of this empirical rule tells us that 95% of the data we have will fall within that shaded area under the curve. That's 2 standard deviations above and below the mean. And the final level is 3 standard deviations. So I'll just continue this shading a little bit. So we've officially gone 3 standard deviations below the mean. Here we're going a full 3 standard deviations above the mean, filling in this. So this orange shaded area now represents 3 standard deviations above the mean and 3 standard deviations below the mean. And the empirical rule tells us that about 99% of the data will be within that distance of the mean when you have bell-shaped distribution. So let's look at an example of where we'd actually compute the standard deviation now. So say we're given a set of data. There are 2 steps for solving for the standard deviation. The first step is to compute the sample mean. Now the sample mean is denoted by x bar, and it's defined as adding all of the data up and dividing that sum by the number of pieces of data you have. So I'll write this out for us. We have 5,500 plus 7,200 plus 7,000 I'll let you watch while I write. Okay, so I've added up all of our data, and that is simply the top portion of our fraction. Now I'm going to divide by the number of pieces of data we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data. So 9 pieces of data. Now, if we do this computation, we're going to reach the number 10,178.88, and this 8 goes on forever. And how we tell ourselves that this 8 repeats forever is we put a little bar over the 8. This value right here that we just computed is the sample mean, and that's a crucial part of computing the standard deviation. So for the standard deviation, I'll give you the 2 formulas that you'll commonly see, and we'll probably just choose one to work through right now. So for the standard deviation, So I'm going to write down the two common formulas for the sample standard deviation. Sample standard deviation is denoted by S. And there's a difference between the sample standard deviation, which is an approximation, and the population standard deviation, which is exact, but we almost never have that exact value. So one of the formulas you'll see, the standard deviation is equal to the sum of the square of the difference. Each data value, x, minus the sample mean. We square this value, and then we divide by n minus 1. And finally, we take the square root. That's the sample standard deviation. But another formula you may see is S is equal to, here we have n times. N is the number of pieces of data we have. So let's just look up here. We have 9 pieces of data. So we can conclude that we have n equals 9. Okay, so we have n times, it is the sum of the square of each piece of data minus, we're going to take a sum of all the data and then square the sum. So notice here, we take x1, we're going to square it, the first piece of data. Add that to the second piece of data squared, plus the third piece of data squared, and so on. This is the sum of the squares of the data. So sum of x squared. That is what we have right there. Here, what we have, the sum of the data squared, we are going to add the first piece of data to the second piece of data, to the third piece of data, to the third piece of data, and so on. After we add all of those pieces of data, we are going to square that value. After we do that, we're going to divide by n times n minus 1. And we're going to finish off this computation by taking the square root. Make that a little bit nicer. So these are the two common standard deviation formulas you may see. Now, which one you choose to use mainly depends on how you go about computing the standard deviation. So if you have a calculator that can easily handle large amounts of typing, there's not a small typing limit for the number of things you can input to the calculator before you press enter, then personally I prefer that formula just because that's what I'm most used to. This formula over here works just as well, and this one may be preferred if you need to separately compute the sum of the squares and the square of the sum separately. Then you can plug each component into this formula on the right a little bit more easily. So I'll go ahead and compute the standard deviation using both of these formulas for you today, just to give a clear example of how we do it, and I'll let you choose what you prefer. So I'm going to copy this data so I can easily plug it into the formula, and I'll be doing some computations live during this recording, so bear with me. Okay, so first we'll do the standard deviation. We'll compute the standard deviation using the formula on the left. So copy this. And what we get here, this is equal to Oh, let me find our mean. Okay, our mean value is right here. Okay, we are going to do a lot of writing right now. So I'm going to put this equal sign below so we have a little extra space. So what we're going to do is the first data value, 5,500. We're going to subtract 10,178.88, so on, square it, plus 7,200 minus our sample mean squared plus 7,889. I'll start writing this so I can make it a little bit smaller. Minus 10,178.88 bar squared. Now, this will count as one line, but I'm going to go ahead and break this up into 3 separate lines. But this all will be the top of our fraction. So plus 8,998 minus 10,178.88 bar squared plus 9,980 10,995 This is the third line of our numerator. Finally, we have the last term is 14,050 minus 10,178.88 squared. So this is the top of our fraction, the numerator. So this whole area is the sum of x minus x bar squared. So put this whole thing over n minus 1. And recall n is equal to 9, so we have 9 minus 1. And now comes the calculator moment. Oh, and the last thing we need to do before we move on is we still have to put this inside the square root symbol. Okay, give me just a moment to find a calculator and plug this in. Okay, so plugging this in the calculator, we are going to have the square root of 5,500 minus after that long calculation, very long, we come up with the number 3074.923594. So that is the first formula that we're using to compute the standard deviation. Now, the second formula requires us to break this into components, different components. And this is easier to do if you have a calculator that does not allow you to type a large number of digits into the calculator at one point in time. So here, I'm going to put down our formula. I'm going to copy this data once again. And here, we will break this into pieces together. So the first component of this calculation, we are going to take the sum of the square of each piece of data. So this is going to be 5,500 squared plus 7,200 squared plus 7,889 squared plus 8,998 squared plus 9,980 squared, 10,995 squared, 12,999 squared, 13,999 squared, plus 14,050 squared. Now, let me warn you, these are large numbers to begin with, and squaring these numbers is going to make them significantly larger. So our result for this sum of the squares is this ginormous number. Okay, that is the result, which appears to be, wow, 1,008,129,252. So it's a big number. Now, the next computation we have is the square of the sum of the data values. So here, I'm going to cheat a little bit. Actually, what I'm going to do is this. I'm going to copy this data. So what we do here is we add all of the data. And after we add all the data, we're going to put parentheses around it and square it. And the number we get here is 839. 239 2100. So this is also a very, very, very large number. But now you can see we've broken this into pieces, and we can pretty easily plug these pieces into the standard deviation formula. So if we do this, what we will get is n, which is 9, times this first large value. So I'll put parentheses around this. Minus the sum of the squares, or the square of the sum of the data, I mean. We're going to divide this by n, which is 9, times n minus 1 is 8. And then we're going to take the square root. And if we do that, what we get is, essentially, if we just round off, we'll get 3074 point. Oh, I'll just write a few extra decimal places. 9235. I'll just round here. 6. So I'm going to round up to 6 for this last digit. And those are the two common standard deviation formulas computed just for you. Now, just to recall, we can compute the standard deviation, which for the data I have sitting here, we computed the standard deviation and found that it is 3074 with a few extra decimal spaces. And we take the standard deviation, and if we want to know how much of this data is within one standard deviation, we have to separately look back at this graph we have and do the computations x bar plus 1 times the standard deviation and x bar minus 1 time the standard deviation, just to get 68% of the data within the mean, and so on. So this was really just supposed to be a quick introduction into what a standard deviation can tell us if we have a bell-shaped distribution for our data. And it was just meant to give you an opportunity to kind of review looking over the formulas and how to use these formulas for computing the standard deviation.